Hello, and welcome to our very first video. Here we are going to derive the integrating factor method for a general first-order linear ordinary differential equation. So we are going to solve this equation at the top of the screen, f prime plus p of x on f equals g of x, where p and g are given continuous functions on some interval I, and f is our unknown function. And our first observation is that the left side of this ODE, f prime plus p of x on f, looks very much like the product rule. Now remember what the product rule says. If I have some other function mu, the derivative of f times mu is f prime times mu plus f times mu prime. And so I look at the left side of my ODE, and in my first term I have an f prime by itself, and in my second term I have an f. So somehow I want to get mu, and in particular mu prime in there, but this is a start. Here is the classical idea. If I have a function mu of x that is non-zero, and I start with my original ODE, f prime plus p on f equals g, then that ODE really is equivalent to a new ODE where I've multiplied both sides by mu. So f prime plus p of x on f equals g. That holds if and only if f prime of x times mu of x plus p of x times f of x mu of x equals mu of x times g of x. And I can go back and forth here from the left to the right or the right to the left because I'm assuming that mu of x is non-zero. And so I can always divide it out and not have a division by 0. So I'm going to work on this new equation with both sides multiplied by mu. I'm going to call the whole equation star for future reference, and I'm going to look at the left-hand side, which of course I abbreviate as LHS. And I want this left-hand side to have the form of a product rule. So the product rule would just be the perfect derivative of f times mu. In other words, I want my left-hand side, f prime times mu, plus p times f times mu, to be equal to the derivative of the product f times mu. So again, what is this derivative of the product? Well, I'll have this equality if and only if I have f prime on mu plus pf on mu is equal to that derivative of the product f prime on mu plus f times mu prime. So this is the equality on the right side that I want to force by choosing mu correctly. And I can simplify this equality already in one way because I have a term of the form f prime times mu on both sides. So we'll get rid of that term, and here's what I want mu to do. I want p times f times mu to be equal to f times mu prime. Now I don't know what f is. Maybe f's going to be 0 sometimes, maybe it won't be. But I can get this third equality, p f mu equals f mu prime, if I just have the simpler equality, mu prime is equal to p times mu. So this is an ordinary differential equation for my unknown function mu, because remember p is given to me at the start of the problem. And in fact, this is also a linear first-order equation, except it's homogeneous. There's no analog of g here. So it doesn't look like I've made my life any easier. I'm still trying to solve a linear first-order differential equation, which is what we started out doing in the first place. But here's where we can use some intuition from calculus, or if we've done separation of variables, we could throw that in. How can I solve mu prime equals p times mu? Well, I'm basically asking for a function that's proportional to itself with a proportionality factor of little p here. So I'm going to let capital P be an antiderivative of little p. I'm going to let capital P satisfy capital P prime equals little p. And then I'm going to put mu of x equal to e to the p of x. And then I do the chain rule. Mu prime of x is e to the big P of x, big P prime of x. That's e to the p of x, little p of x. And then I just remember, e to the big P of x is mu of x. So my function, mu of x equals e to the big P of x, satisfies mu prime equals p times mu. And that is what I wanted. So now I'm going to go back to my post-multiplication equation star and multiply both sides by mu. Here's what I get, just flipping what's on what side of the equal sign around. Mu g is equal to f prime times mu plus p mu times f. But now, this factor p mu I recognize as mu prime. So I have this all equal to f prime times mu plus f times mu prime. And this is, of course, the perfect product rule derivative of f times mu. So now I can integrate. I start out having derivative on the product f times mu equals mu times g. I integrate both sides with respect to x. I will put my constant of integration on the right side. That's a custom I always do, and it's good to have a habit here. Now on the right side, I don't really know what the integral of mu times g is, because I don't have a formula for g right now, but I do know what the integral on the left-hand side is. The integral of the perfect derivative just cancels the derivative out. And so I'm left with f times mu equals the integral of mu times g plus a constant c. And now all I have to do is solve for f. Remember that mu of x is an exponential. Mu of x is e to the p of x, and this is non-zero. So I can solve for f just by dividing by mu. F is equal to 1 over mu, integral mu times g, plus the constant c over mu. Remember, it is very important to keep track of this extra constant of integration when doing this final undoing of the product rule. But you don't really need a constant of integration in finding your integrating factor mu. It would just cancel out from the problem, and I discussed this at length in the lecture notes. This is a nice formula. It will allow us to do a lot of cool theory with these seemingly simple first-order differential equations. But I also discourage you from memorizing it, unless you know it already. I think it's much easier just to find the integrating factor on the fly, multiply through, do the product rule argument, and solve for f. And we will do precisely that in our next video.